Can I help you?
Oh, hey. Hey, you left pretty quickly last time. How do you find the course so far?
Pretty good.
Teacher seems fine.
Yeah, he's good.
Anyway, how was your weekend?
Sometimes,
Oh, bother.
students ask me why I spend so much time talking,
I'll talk to you later.
not about what we know of how perception works, but about how we know what we know, about the methodology used. To be fair, if I thought we already knew everything there is to know about the subject, I would just tell it like it is. This works like this works like that. But fortunately for those of you who want a job in research, there is still plenty of work to be done, and I probably don't have to convince you of the importance of familiarizing yourself with the methods and their limitations. But for all of us, even if you're not here for the science per se, but for the soul knowledge, it is always important to further develop our critical thinking. Learning about what's really going on in the kitchen is the best way to get that done. I have mentioned last time that there are three entities to investigate in the psychology of perception: the stimulation, the nervous system, and the perception. When we study the structure and activity of the nervous system, we use the neuropsychological approach, which we'll explore next week. But the first relationship that we will examine, the subject's perceptual experience of a stimulation, is in nature merely descriptive, because it must be investigated through a behavior, such as a verbal account. Sure, if you ask enough people about their experience, you'll be able to predict the one of future subjects, but it does not explain how perception happens. Still, it hasn't prevented cognitive psychologists to design fancy experiments to infer processes like attention, reasoning, and memory. Just like I've said last time concerning neuropsychology, one could argue that psychology is almost always a study of the faculties. In fact, the way I like to see it is, if the science of psychology was a coin, one side would be the nervous system, and the other side would be the faculties and the emotions. The cognitive faculties and emotions are in essence variables, or categories of phenomena, that researchers thought they saw in their experience and data and gave them names, but we can only grant them explanatory power as far as they are themselves supported by neurological evidence. Fundamentally, the two sides of the coin represent the same whole reality, but from a different perspective. From there, you can study the coin in relation to its external physical environment, like we'll mainly do in this course, or you can study its relationship with other coins and call that social psychology, or even sociology. Now, even though there is still plenty of mystery in exactly how the neural system gives rise to such a rich sense of consciousness, there are no doubt that this side of the coin is the true backbone of the science. This means that no matter how applied we get, we must never forget that the human is fundamentally a cluster of neurons that evolve to gain adaptive faculties in order to act fittingly in its environment. This will become clearer as we progress, and especially if you attend my cognitive psychology course. For the moment, we will go back to a simpler time to attend how psychology effectively broke up with philosophy to start an everlasting association with science. Before the Renaissance, knowledge usually did not come from the investigation of the senses. For the most part, philosophers did not trust what their senses told them, and it was more appropriate to either think their way through philosophical problems using the introspective method, or to rely on ancient texts to provide for answers. Francis Bacon is one of the best-known scholars who criticized this way of doing science. He argued for a radical empiricism based on experiments. Of course, some had greatly predated him, for instance, Ibn al-Haytham. Apologies for my attempts at pronouncing foreign names today. He was a polymath of the Islamic Golden Age. But really, experimental science would need the technological advancements brought by the European Renaissance to truly support it. In fact, the development of the printing press and of better instruments of measure not only helped realize Bacon's idea of a practical science, but also his idea of a science where researchers would work together. Although it turns out that this idea of a collaborative science would bring with it new surprising challenges. In 1795, two astronomers were working together trying to document the exact moment a star would cross the hairline of their telescope. When they compared their answers, they realized there was a half-second difference between them. At first they thought it was a simple mistake, but every time they repeated the experience, they reached discrepant results. This would sadly be the last time these two men worked together. But in the larger scheme of things, what it showed is that Bacon's insistence on observational data is problematic if it does not lead to consistent results. It then became clear that the first step to experimental science would be to understand the relationship between physical stimulation and the variety of psychological responses among people. The empiricist movement of Bacon and the Enlightenment philosophers had only grown stronger when a physician who held the chair of human anatomy at the University of Leipzig, called Ernst Weber, started developing experiments to investigate humans' consciousness in a systematic way. For example, using an instrument that looked like a compass, he was investigating the smallest distance at which the subject reported sensing two distinct pressure points on his skin. He called this the 2-point threshold. In 1834, he published a book called On Touch, Anatomical and Physiological Notes, where he provided charts of the entire body with regards to the 2-point threshold. He made the hypothesis that the differences in thresholds at different spots resulted from the anatomical arrangements of the touch receptors. More precisely, he thought that the more receptors there is for a location, the finer the discrimination would be. Another investigation he made was to identify the smallest kinesthetic difference perceptible, also known as its relative threshold. So he would present a weight to his subjects to use as a comparison point, and then ask them to lift weights of increasing variation until they could detect the difference with the standard. What he was able to conclude from this was that light standard weights required a very small variation to be distinguished from others, whereas heavier standards required a much larger difference. In other words, the variation required was proportional to the standard weight. This seems common sense, of course, that adding 100 grams to the weight of a dictionary would not make much of a difference, but adding that same weight to a pencil would be instantly noticeable. But what really fascinated Weber was the regularity of that proportion across subjects. You see, the ratio of variation to the standard weight to be perceptible was always close to 1/30th when the weights were simply placed on the participants' hands, and that sensitivity increased to 1/40th when they could be lifted. Weber's contribution to psychology thus exceeded the study of the 2-point and relative thresholds, but also revealed that the sense of touch was in fact a bundle of other senses such as kinesthesis, pressure, temperature, and pain. However, his work would be made even more meaningful once a younger colleague from Leipzig called Gustav Fechner would publish his Elemente der Psychophysik in 1860. This would represent the dawn of his school of psychophysics, and would further develop Weber's work. Fechner had been particularly invested in Weber's methodology, because he saw in it implications for the possible resolution of the mind-body problem that had always fascinated philosophers. His own research would focus not on relative thresholds, but rather on absolute thresholds, the minimal intensity of stimulation to be noticed at all. For instance, he meticulously constructed all sorts of experiments to discover from how far we can see a candle's flame on a dark, clear night, or what concentration of sugar is perceptible in a volume of water. Still, the psychophysics were concerned with more than mere thresholds, but with the full extent of the relationship between the physical intensity of a modality and its perceived magnitude. Fechner thought this relationship was always logarithmic, or, as Weber had assessed before him, that as we move up in physical intensity, the sensitivity gradually decreases in a proportional manner. His own experiments on sight and hearing had indeed indicated the same relationship, only with different fractions. Decades later, however, a Harvard psychologist called Stanley Smith Stevens investigated more modalities, and he realized that the logarithmic relationship hypothesis was an oversimplification. Indeed, the perception of length and of electric shocks show respectively linear and exponential sensitivity functions in relation to the physical intensity. He thus formulated his power law, written as the magnitude of the perception S equals the physical intensity I to the power of B, which depends on the modality, times K to account for the unit used. This formula works for sensitivities that increase, as well as those that decrease, because B can be a fractional number, which can then produce Fechner's original logarithmic formula. Stevens also innovated on the front of his methodology. He realized that he could ask his participants to estimate magnitudes of varying stimulation on a scale of their choice. This method would later be used by other researchers to consider if participants could compare the magnitudes for stimulation of different modalities. For instance, would participants be able to match a certain brightness with a loudness of comparable amplitude? It turns out that using Stevens' method, they could, and they did, with impressive homogeneity once more. However, the sense of taste proved to be a bit of an outlier, as some people have a much higher sensitivity than others to certain molecules. The Psychophysic's extensive work on thresholds and intermodal matching was certainly admirable, but their work also tackled the important problem of intrasubject fluctuations. Indeed, they realized that every subject tended to contradict himself, especially when near their absolute threshold. They could affirm that they heard a stimulus of a certain intensity, only to miss it when re-exposed to it mere moments later. The researchers suggested that there must be some fluctuating internal noise in the nervous system leading to this area of confusion, because the experimental conditions were well controlled for any actual noise or distraction. They thus concluded that it would have to take multiple measures for each condition and fix a ratio criterion of detected to undetected stimulations to be qualified as absolute threshold. That criterion was usually 50%, which meant that an intensity detected half of the time was the minimum to be considered absolute threshold. Of course, the presentation of various high intensity would be randomized. This notion of internal noise might seem curious at first glance. It has been shown that people with no sensorial abnormalities do occasionally hear phantom noises or see dull flashes of light in the dark. However, when one sees the wide range of unpredictable activities constantly taking place in the brain when it is supposedly resting, it becomes clear that keeping the perceptual processes perfectly still is not an option. In fact, this fluctuation pervades the whole nervous system. If you try to throw a basketball from far away, or draw a perfect circle, yeah, you may succeed from time to time, but you can't expect to be perfectly constant. The randomizing of trials and the fixation of a threshold criterion is one method to control this type of inner variations, but Fechner also tried other ways to tackle that problem. For example, he tried another type of presentation which relied on alternation of increasing and decreasing intensities. Even in this case, he realized that a gradual increase led to a seemingly lower sensitivity, because subjects tended to wait a few additional presentations to confirm they really heard something. Fechner wasn't born yesterday though, and he realized that by taking the mean of a few series for each participant, he could effectively cancel out the disparity and still save time compared to the randomized presentations framework. If you are feeling a little underwhelmed by these breakthroughs, keep in mind that in the mid-19th century, the mere idea of a scientific study of psychology was raising eyebrows as the mind was seen as immaterial and thus impenetrable. Fechner himself was a dualist, which means that he would see the two sides of our psychology coin as of fundamentally different natures. But he thought that studying how the mind varied in relation to the body was the key to understand how this interaction happens. In this sense, his psychology of physics refers not only to the physics of environmental stimulation, but to the physical alter ego of the soul. In fact, the psychophysics work on seemingly simple problems laid the firm methodological grounds that psychology needed to stand above philosophical speculations in order to attract the attention of promising intellectuals. Now you may take a little IRS to pause on what we've seen so far. After the break, we'll see how the signal detection theory can help us understand how our fluctuating system affects our daily lives. And I'll leave you with a brief outlook of what came after the original psychophysics.